Welcome back, guys. This video is about iterated integrals and partial antiderivatives. This is our first exposure to multiple integration. So let me just motivate this with partial antiderivatives. We've been taking partial derivatives a lot. Let's say you've got a function f of x, y, and you know its partial with respect to x is 2xy plus y cosine of xy plus 1 over x, let's say. And maybe you know that its partial with respect to y is x squared plus 1 plus x cosine of xy. So you've got the partial derivatives and you want to get the function back. Well, if I want to find f, I'm just going to take the antiderivative. But if I take the antiderivative of the partial derivative of f with respect to x, it's not going to give me all of f of xy. It's only going to recover f partially, and I'll show you what I mean. So if I want f of xy back, and I've got the derivative with respect to x, partial derivative with respect to x, I take the antiderivative of the partial derivative with respect to x with respect to x. So I'm undoing that differentiation with respect to x. Now, it's actually very simple. To do this, we just treat y like a constant and we anti-differentiate with respect to x, just like when we were taking derivatives. We treat the other variables as constant and we anti-differentiate this time with respect to that variable. So if my 2 is a constant and my y is a constant, that's just a constant times x, so I bring my constant down. And then I take the antiderivative of x with respect to x. And the antiderivative of x with respect to x, by the power rule, I add 1 to the exponent and then divide by the new exponent. And of course the 2's reduce. Then over here, y is a constant, so I can bring that down. And I want to take the antiderivative of cosine of xy with respect to x, treating y as a constant. Now in order to do that, I have to remember this rule. It was that kx modification of the cosine antiderivative. The antiderivative of cosine in general is sine. But if my angle is not just an x, but it's kx, when I take the derivative of something like this, I have to multiply by the k by the chain rule. If I'm taking the antiderivative, instead of multiplying by the k, I'm undoing that, so I have to divide by the k. So we have to divide by the constant that's inside. So the antiderivative of cosine of xy is sine of exactly the same angle, but we have to divide by the constant. Since x is our variable and y is being treated as a constant here, we have to divide by y. And then the antiderivative of 1 over x is natural log of the absolute value of x. Those y's reduce. Now, careful here, you're probably tempted to just write plus c, and that's almost right. And this is what I meant when I said that we're going to recover f partially. We don't get a constant here. We get something that is constant with respect to x, but it's not necessarily constant with respect to y. So it's going to be a function of y in general. I'll just call it g of y. And if you're saying that doesn't look like a constant of integration, think about taking the derivative of this with respect to x. The derivative of that part with respect to x is 2xy. The derivative of that part with respect to x is y cosine of xy. The derivative of natural log of the absolute value of x is 1 over x. And the derivative of g of y with respect to x is 0. So this is the antiderivative of this function with respect to x. See, it didn't give us f back. It gave us almost all of f, but there's this extra function of y that I don't know. So if I want to find f completely, I want to recover f completely, not just partially, I have to also take the partial antiderivative of the partial of f with respect to y. So f of xy can be represented by two integrals. It's this integral, the antiderivative of the partial of f with respect to x with respect to x, and the antiderivative of the partial of f with respect to y with respect to y. The antiderivative of this x squared, which is constant, with respect to y, antiderivative of a constant is a constant times y. 1 is constant. The antiderivative of 1 with respect to y is y. The x is constant with respect to y, so we bring that down. And then we use this rule again. The antiderivative of cosine of xy is sine of xy, but we have to divide by that constant. Now this time our variable is y and x is being treated as a constant, so we have to divide by the x. And I would want to write plus c, but it's not plus c. It's something that's constant with respect to y, but not necessarily with respect to x, so I'll call that h of x. So f of xy turns out to be x squared y plus sine of xy plus h of x. And both of these represent f of xy. Notice what they have in common. F of xy has an x squared y term. F of xy has a sine of xy term. That's equal to this. Now, in order for those to be equal, the parts that don't match have to match, even though they don't look the same right now. So these match, so we're good there. But this part does not match the rest of this part. So over here, I've got this plus natural log of the absolute value of x plus g of y. And over here, I've got this extra y and this plus h of x. Those have to be the same thing. If these are both f of xy, natural log of x plus g of y has to equal y plus h of x. Well, with that in mind, I think h of x has to be natural log of x, and g of y must be y. And there should probably be an extra constant of integration in there as well. So maybe g of y is y plus c, and h of x is natural log of absolute value of x plus c. So f of xy is this plus natural log of the absolute value of x plus y plus c. Now you should always check, make sure that this satisfies both of them. Is f of xy equal to this plus this? Sure, plus natural log of x plus a function of y. Y plus c is your g of y? Yes, that checks out. Is f of xy equal to that, plus the y there, plus that, plus a function of x? The function of x is natural log of absolute value of x plus c, so it checks out. So that is a partial antiderivative. You'll be doing a lot more of that in differential equations and also in chapter 16. But I wanted you to see, it's just a way of undoing that partial differentiation. But with partial antidifferentiation, we don't recover the function completely, we only recover it partially. There's always going to be that extra function of the other variables that you have to account for. Okay, so that's how we do that. Now, we're also going to be looking at what are called iterated integrals in this section. I want to do a very simple example first. Let's say we're integrating from 0 to x, and let's say 0 to 4. Most of the time in this chapter, we won't be doing partial antiderivatives. We're going to be evaluating definite integrals that look like this. Now, this looks like alphabet soup. It looks much harder than it is, but actually it's pretty simple. We're going to start on the inside and work our way out. Now, if you're wondering, what does that mean, Miss Townsend? We're going to get to what it means in just a second. First, we're going to focus on the computation. I know normally we do concepts first and then computation. We're doing it a little different with this section. We're doing it differently, I guess. It's correct English. Okay. So you work your way from the outside, or the inside out. Now first you anti-differentiate with respect to y, treating x as a constant. So that's a constant with respect to y. So we get x squared, that's a constant times y. And the antiderivative of y squared with respect to y, well, we just add 1 to the exponent, divide by the new exponent. And then you want to substitute in y equals 0 and y equals x and subtract, because these are the bounds for y. This is telling you y starts at 0 and goes to x. Okay. So I replace y with x, and I get x cubed plus 1/3 x cubed. And then I replace y with 0, which gives me a 0, and I just subtract. So we anti-differentiate with respect to y. And then we use the fundamental theorem for y, replace y with 0, replace y with x, and subtract. And now we've got 1 plus 1/3 x cubed, that's 4/3 x cubed, so I'll bring out my 4/3. After you've done that innermost integral, this integral is just a regular integral. It's a regular Calc 1 integral. So we'll bring the constant down and then anti-differentiate, x cubed with respect to x. So we'll add 1 to the exponent and divide by the new exponent, substitute in 0 and 4 and subtract. The 4's reduce, and we end up with 4 to the 4th over 3 minus 0. And I don't know what 4 to the 4th is. Like 16 times 4 is 64, but what's 64 times 4? 256. So you have 256 over 3. And you're saying to yourself, what does that number mean? Okay, now I'm just going to briefly allude to this, and we'll get back to it a little bit later in another video. But here's the idea. In general, we're going to have a function f of x, y, and then this dy dx, it could also be listed as dx dy. I'll just call that dA. We're going to be integrating this function f of x, y over some region R in the xy plane. And so instead of writing it like this, I might write it like this. Now, if f of x, y is positive all the time, or if it's at least non-negative, it's okay if it's 0. We're going to get what's called the volume under the surface. It's the volume between the surface f of x, y and the region R in the xy plane. So this is our z. Here's the region R. And we want the volume under here and above here, above the xy plane. And if you're wondering how we do that, well, we'll see later. We're going to subdivide the x direction into n subdivisions. We'll subdivide the y direction into m subdivisions. And then we're going to put a little rectangle here and a little rectangular prism on top of that. And the volume of that rectangular prism, that's the volume of the ith, jth prism, it's the ith subdivision in the x direction, the jth subdivision in the y direction. It's going to be the height, which is f of x sub I, y sub j, times the area of the base. And that area is going to be delta x times delta y, or sometimes we'll just call it delta a. Same thing. So we'll add these up in the x direction and the y direction, and that leads to a double integral. Now, if f of xy is sometimes negative, so this is for f of xy, that's our z value being greater than or equal to 0 all the time. What we would get in that case, if f of xy was sometimes negative, is the net volume under the surface. So it's a little bit harder to draw, but let's say you've got some surface and maybe it meets the xy plane here. And then over here, it's like below the xy plane. You have to sort of imagine it down here. It's a horrible picture, I'm sorry. What you're going to get is, if this is our region R, let's say we're talking about this rectangle in the xy plane. Maybe that's R. You're going to get the volume above the xy plane minus the volume below the xy plane. So it's sort of a net volume, just like you did net area in Calculus 1. So volume between the surface and the xy plane, so it's going to be the volume below the surface and above the xy plane minus the volume above the surface, so the surface is down here, and below the xy plane. Now normally we don't say above this, we don't reference the surface, so we would just say a volume above the xy plane minus the volume below the xy plane. So it's a net volume. Okay, so that means that this actually represented a volume under a particular surface. That's z equals x squared plus y squared, that's our elliptic paraboloid, over a particular region in the xy plane. So these bounds describe a region. So for our example, we had the integral from 0 to 4 of the integral from 0 to x of x squared plus y squared dy dx. Well, this tells me these innermost bounds go with the innermost variable. These bounds tell me that y is between 0 and x. And these bounds tell me that x is between 0 and 4. So the region in the xy plane looks like this. If I want to sketch that region, I need to sketch really 4 curves. I want to sketch y equals 0. Well, y equals 0 is actually the x-axis. Y equals x, that's this. X equals 0, that happens to be the y-axis, and x equals 4, that's here. So our bounds are y equals 0, y equals x equals 0, x equals 4. So the region that we're integrating over is actually that region in the xy plane. That's the region R. You're saying, how does that a volume again? Well, that's the xy plane. This integral, we evaluated it earlier, it was 256 over 3. What that represents is the volume under the surface given by z equals x squared plus y squared. It's our elliptic paraboloid. Here's the x-axis, there's the y-axis, and then we've got a little triangle like this. x equals 4 might be here. Y equals x is a line that looks like that. It's going to meet over there at y equals 4. So what we're finding is the volume under this surface and above that little triangle. I know it looks a little strange, but it turns out that the volume above this triangle and below this surface is 256 over 3, based on our calculations from earlier. Okay, so we're going to get back to this volume under the surface bit a little bit later, but what I really want you to see is that region R that we just came up with. This region R can be described differently now. Instead of finding the area of this region by integrating from 0 to 4 and just integrating y equals x to find the area under the curve, we can describe this region R with a double integral. This double integral is it. We've got y, and y goes from 0 to x, and x goes from 0 to 4. So if I just wanted the region R, the area of the region R, it's going to be the double integral over R of dA. And one way that we can describe that is to integrate with respect to y first and then x. Y goes from 0 to x, and x goes from 0 to 4. And there's also another way that we can describe that, dx dy. Now, the way this works is these innermost bounds go with the innermost variable, but I can't just flip these. The innermost bounds have to go from a function to a function, and the outermost bounds go from a constant to a constant. Like, these bounds come from drawing rectangles that are vertical. You might be saying, well, what is that? How is that true? Well, let's look at this. So there's a rectangle. It's a vertical rectangle. Y starts at 0 and goes to x. And as y goes from 0 to x, x goes from 0 to 4, and we get the entire rectangle. So y goes from a function to a function, and x goes from a constant to a constant. Now, when I do the dx dy integral, I want to draw my rectangles the other way. And I want x to go from a function of y to a function of y. And I want y to go from a constant to a constant. Let's do the constant part first. It's easy to see. If that's y equals x and this is x equals 4, well, that must be y equals 4. So y goes from 0 to 4. And x goes from this function to this function. The smaller x value is on the left, so this is going to be x on the left to x on the right. It's left to right. X on the left is x equals y. So x is between y on the left and 4 on the right. So the bounds for x are y and 4. The lower bound is y, and the upper bound is 4. If you evaluate this integral and you evaluate this integral, you're going to get 1/2 base times height, the area of that triangle. So you're going to get 1/2 of 4 times 4. So 1/2 of 16, you're going to get 8 for both of those. You'd say, why would I do that? I could just find the area using 1/2 base times height, or I could, just use a regular Calc 1 integral. I agree. The reason why we want to do that is because of this, because of where we're going. If I integrate under a surface, or if I'm integrating a surface, like we're doing right here, we're finding volume under a surface. The region R that we're integrating over needs to be described like this, with this variable going from a function to a function, and this variable on the outside, the outermost variable, goes from a constant to a constant. If that works, if that holds, when you're done, you'll get a number, and that number will represent a volume. If you put a 0 and an x on the outside, you're going to end up with a function of x out there. It doesn't make any sense. One other thing that you should know about setting these up, and we're going to set a lot more of these up in the next video, is that this y value is going from a function to a function. It can't go from a function of y to a function of y. We're saying y equals something. Y equals this function, y equals this function. So the bounds for y, the bounds on the inside, can depend on the outside variable. So y is going to go from a function of x to a function of x, and x goes from a constant to a constant. Or x goes from a function of y to a function of y, and y goes from a constant to a constant. So let's write that down, and then we'll do more examples in the next video. So let's avoid talking about volume for right now. We'll get back to volume in a minute. But let's say we're trying to represent areas with double integrals. If you're looking at something like this, y equals f of x and y equals g of x are here, and x equals a is here, and x equals b is here. Y goes from a function to a function while x goes from a constant to a constant. So it would make sense, if I'm trying to describe this area, it would make sense to integrate with respect to y first. So y goes from g of x to f of x, goes from the bottom function to the top function, and x goes from a to b. So these bounds tell me that y is between g of x and f of x. And again, this is the bottom function for y. And f of x is the top function for y. And then these bounds, on the outside, they go with the outermost variable. They tell me that x goes from a constant to a constant. Okay, so that's one way we could describe this area, and we might be integrating over this area later, which is why we'd have to represent this area in this way. Now the other possibility is you might have x as a function of y over here and x as a function of y over here, and y going from c to d. So we've got x on the left, x on the right. This time, since x is going from a function to a function, I'm going to draw my rectangles horizontally rather than vertically. And I integrate with respect to x first and then y. Let's do the easy part first. Y goes from a constant to a constant, so it goes from c to d. X goes from the smaller x values to the larger x values. In this case, the smaller x values are g of y, are given by g of y, and the larger x values are given by f of y. So I've got x is between g of y and f of y, and this is our left function, and this is our right function. It's just smaller to larger, generally. But remember, smaller x values are to the left, larger x values are to the right. And then these bounds tell me where y starts and stops. And we're going to do a lot more of that in the next video when we talk about areas of regions. One last thing before we move on. Now, if the functions actually look like this, it's pretty obvious how you have to integrate. You integrate with respect to x first and then y, or y first and then x. If you've got a region like this, there are many regions that can be described both ways, and then it's really up to you. This way and this way are equivalent. You're still going to get the same area of the region. You're still going to get 8 for the area of that triangle. But there are 2 different ways we can represent that. Now, one of these representations might be better depending on what the integrand is, but we'll get to that later. But my point is, for right now, if it looks like this, do dy first then x. If it looks like this, do dx first and then y. If it's ambiguous like this, you can usually do it both ways, and either one is fine.